Okay, recording. All right, so this is the first lecture. So this is where we actually start getting into some of the material for the class. And this first lecture is going to be on measurements and significant figures, which is something we'll come back to a lot throughout the semester. So let me get started by pulling up the PowerPoint here. All right, let's get this started. All right. So you may be used to units. Traditional units that you see are ounces, yards, pints, cups, right? All these different units. And a lot of times we're converting between different units, go from pints to cups, or liters to gallons or whatever. And in science, or in chemistry at least, there's a lot of conversions that go on. We try and mainly stick to scientific units, and we'll talk about those in a little bit. But you'll still see a lot of other units that you're going to have to convert between, and we're going to go over that in a later lecture. Right now we're just going to kind of get used to scientific notation and how we look at numbers and stuff like that. So let's see. So SI units, those are like the scientific units that we use. So time is in seconds, length is in meters, volumes in liters, mass is in grams, and temperature is generally in Celsius or Kelvin. So that's usually what you'll see it in. And a lot of the formulas that we use are going to be using these units. So we'll need to be comfortable converting, for example, from feet to meters and stuff like that, which we'll get into. But first off, we'll start out here. So, I mean, the goal, and it would be really nice if we could just use the same unit for everything, right? But here we're gonna look at some different measurements and see why sometimes that poses a problem. So like the average height of a person is like 1.5 meters. Then like if you were talking about the distance from here to your apartment, 1,000 meters, distance to the moon, 380 million meters, right? Your thumb, length of your thumb, 0.05 meters. Distance between hydrogen and oxygen in a water molecule. I don't have that off the top of my head, but a lot of zeros. And basically, the problem that you run into, right, is that these can get really hard to read and hard to interpret. So even if you might know what a meter is in your head, right, it's about 3 feet, you can kind of estimate that. If I said 0.05 meters, it's going to be really hard to kind of estimate that distance. Unless I told you 0.05 was the length of your thumb, then you could just look at that. But anyway, so large and small numbers can get really awkward once you get out of the realm of the, for example, like with meters, if you go anywhere past like 1 in 100, it starts to get a little weird. And so one way to get over this is to use scientific notation. So if you're not familiar with scientific notation, it's a way of basically getting rid of the zeros. So for example, let me see if I can pull up the pen here. So for this 1,000 right here, okay, we have 3 zeros, right, on this one. Oh, sorry, I'm getting used to my pen. It might take me a couple lectures to figure this out. We have this 1,000 here, right? So 3 zeros. To get to 1,000, you would do 10 times 10 times 10, which is 10 to the third. So 1,000 could also be written as 1 times 10 to the third power, right? So scientific notation allows us to focus right here on this 1, and then you can throw in a power of 10 in order to get rid of all these zeros. Okay, so The way I kind of imagine it, right, is, for example, if you look at 100, this is really 100 with a decimal by it. So you move the decimal over until you just have one digit, okay? And I move the decimal over 2 to the left, which means you're gonna have 10 raised to the second power, or 10 squared, okay? So this is equal to 1, which we put the decimal here, right? 1.00 times 10 squared, okay? So when we're converting a number, that's basically what we do. And you can kind of go through and look at these. When you go the opposite direction, you'll actually need to be moving the decimal over to the right in order to get the decimal to the right of the 1. And so that ends up being 1 times 10 to the negative 2. So when you have to move the decimal over to the right, you would raise it to the negative power of however many spaces you move the decimal over. A quick way to check this, like on an exam or homework, is just to punch it into your calculator. So if your calculator is in decimal mode, you can put 10 to the power of negative 2, and it should give you 0.01. And so you can check your scientific notation just by like entering this into the calculator and make sure that it actually shows this number if you're trying to convert from the decimal form over to scientific notation. So just as another quick example, let's say you have 1,200, okay? And we want to convert this into scientific notation. So if we imagine there's a decimal point here, right? Because there is, because yeah, 1,200, this is the ones place, so it'd be followed by the decimal. So in order to convert it into scientific notation, remember we want a number that just has one digit here in the ones place and none to the left of that. So we need to move the decimal over 1, 2, 3 times, okay? And that actually would give us 1.200, okay? If we move the decimal over 3 places. And since we moved it over 3 places, we now have 1.200 times 10 to the power of 3. So if you put this number in your calculator, it should give you back 1,200, okay? So go ahead and do a little more practice on that scientific notation if you need some more practice, and there should be some problems in the homework as well. That will help you get some practice on converting easily between the whole number, or the in some cases it may be a decimal number, into scientific notation, and vice versa. So back and forth between the two. Let's see, yeah, so scientific notation, again, it gets rid of the zeros. For this distance to the moon problem right here, this is a really long number, and just looking at it kind of makes you just not want to even think about it, right? So to convert this number to scientific notation, we put a decimal point here, and then we need to move the decimal point all the way over until there's just one more digit left to the left, right? So we come 1, 2, 3, 4, 5, 6, 7, 8, okay? So then that gives us the 3.8, okay? And we just leave off all the zeros, right? Because 3.8 is the same as 3.8000000. And since we moved the decimal place over 8 positions, that puts the 8 right here. So 3.8 times 10 to the power of 8 meters looks a lot easier to digest than this big number. And going the other way, so for the HO bond distance in water, like we talked about, we got to move the decimal over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spots to the right. Okay, to put the decimal just to the right of this 1. And we're going to get the 1 there. And since we move the decimal place over 10 positions to the right, we have a negative 10 in our exponent. And again, if you're kind of confused on whether you should do a negative or a positive here in the exponent, just practice is going to help. But again, you can, if you thought it was positive, put it in your calculator, and you would see that you would not get this number. So then switch it to negative, put it in your calculator to check, and you could get this number. So that's an easy way to check if you're doing these problems right as you're working through them. Sometimes instead of using scientific notation, we just use a different prefix. So here's some prefixes that you may not be terribly familiar with. Peta, tera, giga, mega, kilo. Kilo you might know from like kilogram, right? So this is 1,000. Numerical value is 1,000. So 1 kilogram would be equal to 1,000 grams. And mega, giga, tera you might know from like megabytes, gigabytes, and terabytes, right? So each one's increased by 1,000. So these are some prefixes that we'll get into a little more as we move on. And there's some tables that you'll probably refer back to as you use them. But for example, the way that I like to kind of think about it is you use this numerical value here. So let's say you have 1,200 grams, okay? So 1,200 grams, we know that there are 1,000 grams for a kilogram, because the numerical value of kilogram is 1,000, right? 1,000 grams is equal to 1 kilogram, okay? So you can use this number to convert between grams and kilograms. This is something that I don't want you to worry about too much right now, because the next lecture is when we talk about the conversions between units, and so we'll go over this more. But just recognize that there's two different things that we could do from this grams, right? We could say this is equal to 1.2 times 10 to the third, let's see, 10 to the third grams. Okay, that would be just simply changing this number into scientific notation. Another thing that we can do, we could take 1,200 grams and we can convert it, which is something we haven't talked about, over into kilograms. And so we'll talk about doing that in the next lecture. Okay. So here's just some more prefixes again that we'll worry about more as we move into the next lecture as far as converting goes. But right now would be a good idea to start learning the different prefixes and the values that they hold. So there's some charts in your book that you can look at for that. Let's see. Oh, this is generally when I do a demo in the class. Unfortunately, I don't have like all the stuff to do the live demo, so we'll have to skip this portion. All right, so now we get into numbers and measurement, and this is where we start talking about significant figures. So to understand why we even have significant figures, I'm going to go through this exercise, okay? So if I asked you how many ping pong balls are on the slide, I think everyone would say 3. I hope everyone would say 3. We have 3 different ping pong balls, right? There's really no debating this, right? There's 3 ping pong balls. A different exercise though, I could say, what is the length of this? Looks like a piece of wood, okay? And you're measuring it with this ruler on centimeters. Is it 2.99? Is it exactly 3.00? Is it 3.01, 3.02? That would be hard to say, right? We can kind of see that the board is a little bit above the 3 centimeter mark. And so I would pretty easily rule out A and B, but I don't know if it's 3.01, 3.02, or 3.03 just by looking at this picture, right? And so this is where we get into significant figures. In a lot of measurements, you're going to have some numbers that are exact, or some numbers that you are confident on, I should say. So in this measurement, for example, we're confident that it's at least 3 because you can see that it's above the 3 mark. We are, however, not confident on the rest of the digits in this one. So we're going to talk about kind of how we make these measurements in chemistry, and significant figures is kind of the term we use to describe how many figures in a given measurement are actually, how many digits in a given measurement we're actually confident on. Okay, so we kind of talked about the ping pong balls and the 3 centimeter measurements. So how confident are you that we have exactly 3 ping pong balls? I'm very confident. How confident are you that we have exactly 3 centimeters? I'm not confident, okay? And so measurements will contain error. If you're counting something, it doesn't contain error, right? Unless you count wrong. But for the most part, there's not really room for error. Measurements, though, they do contain error. So 2 terms that you'll kind of hear me say as we go through the lectures is exact numbers. That's one term. And those are numbers that are defined or exact, okay? So counting, like I said, that's an exact number. Defined quantities, 12 inches per foot. By definition, 1 foot is 12 inches, okay? By definition, 2.54 centimeters is an inch, okay? Sometimes conversions between units can be, sometimes they're considered not to be exact, but in this case, in those cases, I'll tell you, right, if it's exact or not. But when you're converting between centimeters and inches, it has been like defined as 2.54 centimeters equals 1 inch. So anyway, when it's defined, then you can say it's exact. When it's measured, then there's some amount of error in that measurement. And it depends on the precision of the measuring device, okay? So, for example, let's see. Okay, so, oh yeah, sorry. So if we're looking at the measurement of this piece of wood on the ruler, our uncertainty is that we know it's greater than 3 centimeters, but we also know it's less than 3.1. So the first tick here, that represents 3.1 centimeters. And so we know it's a little bit less than that, but a little bit more than 3.0 centimeters. We don't really know exactly, is it 3.02, 3.03, or 3.04? We can't really say that. So whenever you have a number, a measurement, okay, oops, sorry, okay, so when you have a measurement like this, the last digit we refer to as the estimated digit, okay? This is the final digit and it contains a small amount of error. These 2 digits right here, these ones we're certain about. So I guess we could say exact digits, okay? All right. So those ones we're sure about. This last one, we're not so sure. That one's estimated, okay? So when you see a measurement, that's kind of what's going on there. So this gets us into significant figures, and this is really one of the biggest things you need to learn from this lecture. Significant figures tell us how many of the numbers actually mean something, right? For example, or I guess, sorry, we'll get into examples after we go through these criteria. So these are just 4 criteria that will help you determine whether a figure is significant or not. So anything that's not a 0 is always considered significant. If it's a 0 between 2 different significant figures, it is also significant. A 0 that follows a decimal and a significant figure is significant, and the 0 that follows a significant figure and is followed by a decimal is significant. So this is going to take a little practice to like get this criteria down. Just hearing it was kind of confusing, but we'll go through some examples. Okay. So for example, the world population. So if it's reported like this, okay, 6,721,000,000 people, okay, world population. Now, obviously, this is not totally exact because people, even if they could count, by the time they could count all the people, somebody's probably died and 2 people were born, right? So this is not going to be an exact number. This is just an estimation. So when it's as written, we look at the number of significant figures that it has. So this number has 4 significant figures, okay? Sorry, 4 significant figures. And the way I know that is, so if I look at the criteria, non-zeros are always significant, okay? So that means this 6, this 7, this 2, and this 1 are significant. So that's 4 significant figures. Then the zeros is where sometimes we're not sure if they're significant or not, and so that's when we need to look at the criteria. So if we look at the criteria, any 0 between 2 significant figures is significant, okay? So this 0 right here, it has a significant figure to the left, but the 0 on the right of it is not significant, okay? So this 0 is not significant. A 0 following a decimal and a significant figure is significant. Well, these zeros do not follow a decimal, so they're not significant. So we already know all the zeros are not significant, right? But we can go through all these. A 0 which follows a significant figure and is followed by a decimal is significant. These zeros follow significant figures, but they're not followed by a decimal point. There's not a decimal point here. So that means that these zeros are not significant. So the only significant numbers in this number are these 4 digits right here. And we remember the last digit, that's estimated. Okay. Oh my goodness. Sorry, I'm gonna get better at this pen thing, I promise. And then these 3 digits right here, those ones we can count on, okay? Those ones are exact. Okay, sorry. Those 3 are exact. So what that tells us is we're sure there's about 6,720,000,000 people. And this 1 right here is where the estimation comes in. So if we ask, where is the error in this number, right? It's at this 1 spot. So you can say plus or minus 1,000,000 people, right? So this kind of tells us that the error is in this digit. So this digit could be 2, right? This could be 0, okay? That's generally where you're at with that last digit. Technically, this digit, because it's estimated, could actually be plus or minus maybe more than 1,000,000. But what's really important is just that this digit, this millions place, right? This one is estimated, okay? So we can say that this number is accurate only to the tens of millions. Any claim about, you know, a 2 or a 3 here is just an estimation on somebody's part. Okay, so then the length of an OH bond, right? If you read that it's reported like this, okay, then we look at the how many significant figures are on here. So let's dive into that. So this 1 is significant, right? Because it's a non-zero. So this is a significant figure, this 1 right here. I'll put a little check mark. Okay. Now we need to decide if any of these zeros are significant. Okay, so all these zeros, we can say, are between a significant figure, and a decimal point, right? If we're looking at the zeros that are between the decimal point and the 1, they don't meet any of the criteria here, okay? So this one says a 0 between 2 significant figures, okay? Those zeros aren't between 2 significant figures. The only significant figure was the 1 on the far right. 0 followed by a decimal, or sorry, a 0 following a decimal and a significant figure. Those zeros followed a decimal point, but they did not follow a significant figure, so they're not significant. And then a 0 which follows a significant figure, which those do not follow a significant figure, so they automatically don't qualify for this third one. So the only significant figure here is the 1. Check mark back up there. Okay. And since it's the only significant figure, it's also the final digit, right? The final significant figure. And so the error is actually in this 1 place right here. Okay, and that's where we see the error. Okay, and you might be wondering, like, why do we care about where the error is? I mean, one important part is just like when you hear a number, you can tell yourself that, okay, you know, this number right here has 4 significant figures, and it's not exact in all these zeros, right? It could be plus or minus a few million, basically. And so that's one reason why it matters. But then also when we get into calculations with significant figures, you'll see why we can't, why we need to know how many significant figures are in there, because it helps us determine with how much accuracy we can report our answers. So again, we'll talk about that in the next lecture. Okay, so this is kind of just, again, going over how many significant figures are in each number. Okay, so yeah, so here's an interesting case, right? So let's say the world population was calculated, and whoever did the calculation actually knew that it was significant within 10,000, right? Because the number as reported, like we said, we could only believe that it was significant within 1 million. But what if these zeros, like this one's actually true, right? We want to say, no, we know for certain that there is a 0 here, and that we're just really not sure up to this point, right? So plus or minus 10,000, right, or 20,000. So we need to be able to put this into a number that can correctly report the error that we have. And so in these cases, scientific notation comes into play. Okay, so if you have this number and you know it's significant up to this point, then you actually have 6 significant figures, okay? So 1, 2, 3, 4, 5, 6. All those are significant because you know when you took the measurement, right? When you took the measurement, you knew that these numbers here were significant, right? And that you just estimated this last digit. So then we'll use scientific notation. Okay, so in order to do that, what we want to do is just, again, to convert this into scientific notation, we move the decimal over 1, 2, 3, 4, 5, 6, 7, 8, 9 spots. Okay, and so ignoring all the zeros on the end, we could write the number as this, but that one's incorrect because this right here shows 4 significant figures when we really want to report it to 6 significant figures. And so if we add in these zeros, then we have 6 significant figures. So in this case, the 6, the 7, the 6, the 7, the 2, and the 1 are all significant because they're non-zeros. And then these 2 zeros are significant because, I'll go all the way back here. Any zero, let's see, which one is it? Any zero following a decimal and a significant figure is significant, okay? So these zeros follow a decimal and they also follow a significant figure, so they are significant, okay? So that gives us 6 significant figures. Cool. All right, so if you want to just pause the video, you can try and do these on your own, okay? Try and determine how many significant figures are in each of these. All right, so let's just go through them. So let's see if I can find my pen here. So in this first one, we know the 6 and the 7 are significant because they're non-zeros. Okay, and then any zero that is between 2 significant figures is also significant. Okay, that should be in our criteria. Let's see. The second one, right? Any zeros between two significant figures are also significant, okay? Okay, so that gives us that one. All right, so the 6, the 0, and the 7 are all significant. This last 0 is not significant, right? It's not between two significant figures, and it doesn't follow a significant figure and a decimal, right? And then the third criteria is that it follows a significant figure and is followed by a decimal, and there's no decimal at the end here. Okay. All right. 60.70. Okay, the 6 is significant, the 7 is significant, the 0 is significant because it's between two significant figures. And then this last 0 here is also significant because it's after a significant figure and after a decimal. Okay. So on this third one, 6 is significant, 7 is significant, the 0 is significant because it's between two significant figures. The last 0 is significant because it follows a decimal and a significant figure. These two zeros, though, are not significant because they don't meet any of those other criteria, okay? And this last one, the 6 and the 7 are significant, and the 0 is significant because it's between two significant figures. And then these 3 are not significant as well, and you can look at the criteria to see that. Okay, so we got 3 in the first one, 4 in the second, 4 in the second, and 3 in the, 4 in the second, 4 in the third, and 3 in the fourth one here. Okay. So some people may prefer to use scientific notation to determine how many significant figures are in the number. So in order to do that, you're just going to convert this into scientific notation. But I mean, personally, I think it's easier just to use the criteria, so that's what I'll be going through when I go through the lectures and stuff like that. Okay, so just a quick little quiz, see how we're doing. How many significant figures are in the following number? Okay, so go ahead and try this out. Okay, so here we go. So let me find my pen. Okay, so the 5 is significant because it's a non-zero, okay? And then we look at this 0, it follows a significant figure and it is followed by a decimal. So this is that third criteria that doesn't come into play that often, but it does mean that this 0 is significant. This 0 is also significant because it follows a significant figure and is followed by a decimal. So the reason, I know this looks weird, you would never really write 500 decimal with nothing else after it, but you do use it in chemistry sometimes to show that this 0 is significant, right? Because if I just write 500 milliliters, as written, all this has is one significant figure, okay? One significant figure. So if you actually did this measurement of 500 milliliters and you used a measuring tool or a graduated cylinder that allowed you to measure with accuracy that you actually have 500 milliliters, then you want to report that you actually are confident you have this many milliliters, right? If you just report 500 milliliters like this, somebody's going to think, oh, it's like 500 milliliters plus or minus, 10, 20, 30, something like that, right? That means that this digit you wouldn't really be certain about, right? Or whatever. So that's the reason that you would use a decimal, because by using a decimal, you tell people, okay, I'm confident we have 500 milliliters plus or minus like 1 or 2 because this is your estimated digit, right? Okay, so we should have 3. Let's see. Yep, 3 sig figs, okay. Alrighty, I think that might be the last slide. Yep, it is. Okay, so stop sharing here. Okay, so that was the not the last lecture. That was the first lecture of material you need to know. So go ahead and review that as much as you want. Use it while you're doing the homework, and let me know if you have any questions or if you feel like I didn't explain something in a way that you were able to understand it. Email me or visit with me in office hours, and we can go over it. Okay, and then make sure to take the lecture quiz on Learning Suite after you watch this lecture, just to mark that you watched the lecture. Okay. All right, we'll see you next time.